These are the notes for lesson 2.2. This is just the first part of lesson 2.2, so we will have another session. So part B of lesson 2.2 will be a separate video. In this lesson, we want to talk about identifying a polynomial function as well as evaluating a polynomial function at a given value, x value, using substitution. So we're just going to be using substitution, basically plugging in a number and finding the value of y, or the value of the function. But before we get started into the substitution, let's just take a look at what polynomial terminology we need to know. And so you need to know that a monomial is a single expression consisting of a number, a variable, or a product of numbers and variables. And remember that the word mono means one. So a couple of examples are 3x squared. That's a single expression consisting of a number and a variable. And these are multiplied, of course, so that's what we mean by product. And then sometimes you can see a monomial as just a single number, like 17. Or you could see something that looks like this, x to the third. So those are all separate examples of monomials. And when you add or subtract multiple monomials together, it's what you call a polynomial. And so poly means many. And a few examples of that would just look like this. So we're taking monomials and we're smashing them together using the operation symbols like plus or minus. Okay, so there's a polynomial. And that one happens to have 3 terms in it, so that would be a trinomial. And then we also have something that could look like this with multiples. Besides just 3 terms, we could have a lot more terms than that. There's 3 terms. What if I added a 4th term, like adding 6, or I could subtract 6 or whatever, but we could say this is a 4-term polynomial, or generally we just call it a polynomial. You don't have to call it a 4-term polynomial. All right, and then we have some things that we want to know about polynomial functions. So here's the general or standard form. Polynomial functions only have exponents that are whole numbers. Okay, so remember back to when we were talking about sets of numbers, whole numbers are non-negative. Okay, so the exponents cannot be negative. And they do start with 0. So 0 is in the set of whole numbers. So there's some examples of what we mean by whole numbers. Okay, they can't be variables, they can't be negative, but it could be anywhere from 0 all the way up, whole numbers. And those are the exponents that we're talking about. All right, polynomial functions are in standard form when terms are written in descending order. Okay, so if you notice the other polynomial that I wrote above, that was in descending order of exponents from left to right. All right, so we're going to take a look at that in just a second, from left to right. So if I go back up here, this is the standard form of a polynomial when you can see that 4, 3, 2, notice that those are going in descending order from left to right, and that's how you want to arrange any polynomial that you write. That's the standard form. All right, let's take a look at the next page. All right, and on this table we have common polynomial functions. I'd like you to know the name of each of these types of functions, and then also the degree. The degree has to do with the exponent. So the exponent in a constant function is 0. And an example of this would be that y is equal to negative 14. That's just an example. So if I go over here and try to draw a graph of this, a graph, let's say this is x, this is y, and if I was trying to graph x is negative 14, sorry, y is negative 14, then at negative 14 we would see an exactly straight line going in a horizontal direction. And then if we have a linear, okay, that's to degree 1. Notice that in this expression, or this equation, I don't have any exponents either. And so this is a linear. Remember, it's just going to be a upward sloping line or a downward sloping line, depending on if there's a negative sign in front. So let's go ahead and give an example of what this graph might look like. Okay, so this would be crossing at -7 down under here, but it is positive in slope, and it's kind of a steep slope because 5 generally makes it pretty steep, but we would have just a straight line. And even if that's not super straight, this would be crossing here at -7. All right, so we know it's a line because it is of degree 1. Now, last semester, we studied about quadratics quite a bit, and quadratic functions have a squared term. So y equals 2x squared plus x minus 9. That is what we mean by a quadratic because it has this x squared term. And remember, when you were graphing these were always in the shape of a U, whether it was downward shaped U or upward shaped U. Let's just go ahead and draw one in here. This may not be exactly this because I'm just going to give you an example, but the shape of the graph, remember, is called a parabola. And this one has to be facing up because there's a positive coefficient in front of x squared. If we had something that was like y equals -2x squared, then that would be the downward shaping parabola. And you probably remember that from last semester. All right, so cubics are new to us. We have not done any work with cubics. And cubics, this would be an example of an equation that would be called a cubic. X cubed minus x squared plus 3x. Notice that the highest degree here, the highest exponent number is 3, and that's where we get the degree of the polynomial. All right, so let's take a look at what this graph might look like anytime you have a cubic, and that would look like this. So notice that that's part of a parabola, but then it also goes in the downward direction like that. So that's what we call a cubic or third degree polynomial. So I'd like to introduce the last one is quartic. A quartic polynomial has the degree 4. It's a fourth degree polynomial. And let's make an example here. So y equals x to the fourth plus 2x minus 1. So as long as the highest exponent number is 4, we call it a quartic. And the graph here is going to look a lot different, although it kind of looks like two parabolas smashed together. So let me give you an idea of what this looks like. It looks like this. Now we know that it's going to be upward facing because notice that the term here has positive. There's no negative number. If there was a negative number, so let's just say it was -x to the fourth plus 2x minus 1, then we would have a graph that looks more like this, and it would be downward facing, and that's similar to what we know about parabolas as well. So it's important for you to know all these terms and kind of how it works because we are going to be taking a look at the example here where it says identify polynomials, identify polynomial functions, determine whether each function is a polynomial function, and if it is, then you want to write it in standard form. Remember, that's in decreasing exponents, the numbers should be decreasing, and state its common name, which is on the table, and also state its leading coefficient and its degree. So you have a lot of things to do if you can determine that it is a polynomial function. Just remember, it is a polynomial function if it has a whole number exponent, okay? All of the exponents have to be whole numbers, so anything from 0 on up, okay? It cannot be fractional. It can be 0, but it cannot be negative. So the first thing we want to do when we look at these is determine if it is a polynomial function, and in this case for problem A, it is a polynomial function, and we need to write it in standard form. So standard form means that we need to take this term, this whole term, and put it in position correctly. So it needs to be before the plus 3. So we need to rewrite this. H of x equals x to the fourth minus 1/2 x to the second. We're writing them in decreasing or descending order in terms of the exponent, plus 3. Okay, so we did this part. We did it in standard form. And now we also need to state its common name. Well, the common name comes from the degree. This is a degree 4, or we could say fourth degree, quartic. Remember, that's the common name or the standard, the common name. And its leading coefficient is 1 because there's not anything there in front of the x, so the leading coefficient, or LC, is going to be 1. And that's all you have to do. So let's look at problem B. Problem B gives us this information, 7x minus the square root of 3 plus pi times the square root of 2. Well, it looks like all of our exponents are positive. We don't have any negative exponents, so this again is a polynomial function. And let's go ahead and rewrite it. This one is g of x equals, and we need to bring this whole term to the front because we have to write our exponents in decreasing order. So pi x squared plus 7x minus square root of 3. The term that doesn't have a variable, like this one right here and this one right here, if there's no letter with it, then that's our constant function. That goes last. Okay, so this one didn't have a exponent, although we know that really there's an exponent of 1 right there. So we have to write them in decreasing order, remember. So we've done the standard form, and now we need to state the common name. The common name of this one is just a quadratic, and we could say this is a second degree quadratic function. Oops, quadratic. And the leading coefficient, once you get it in the correct form, the standard form, the leading coefficient here is pi. So the leading coefficient just means the number in front of the very first term. Okay, so the last one here, it looks like we have a negative exponent, so therefore this is not a polynomial function. And because it's not polynomial function, we do not have to do any more work. We just have to determine that it's not, and the reason it's not is because it doesn't have a whole number exponent. The directions got printed on the bottom of this page, so these are the directions for the next page. It says determine whether each function is a polynomial function, so let's go ahead and look at those. And if the function is a polynomial function, write it in standard form, state its common name, name its leading coefficient, and give the degree of the function. So I'm going to give you a little hint here on these because I'd like you to finish these on your own. There are 2 here that are no, they are not functions. So here's your hint. 2 of the 6 that you see, 2 are not polynomial functions, and 4 of them are polynomial functions. Okay, so you tell me which ones they are, and then the 4 that are polynomial functions, make sure you finish by doing these steps up at the top. All right, let's go ahead down here to part 3, example 2. It says use direct substitution to evaluate h of x at the given x value. So each time in each of these problems, we are given what x should be replaced with, and so we are going to substitute in the number that they give us. So what I was planning to do is do the problems A and C, and then I'd like you to do the B and D problems on your own. And these are pretty simple to do. You might want to have a calculator with you. When I plug 3 into each spot for x, this is how it's going to look. So function h, when I plug 3 in, that's what this means, h of 3, I'm going to write 3 for x each time I see an x. So 2 times 3 to the 4th minus 5 times 3 to the 3rd minus 4 times 3 plus 8. And then I just need to work that out. So I basically have to rewrite this again. So 2 times, what is 3 to the 4th? Well, 3 to the 4th, when you use your calculator, is 81. And then 5 times 3 to the 3rd, what is 3 to the 3rd? 3 times 3 times 3, so that is 27. And this is a multiplication dot, sorry. Minus 4 times 3, which is 12, plus 8. Okay, and when I put all that into my calculator, there's quite a bit of number crunching here, so you're just going to want a calculator. 2 times 81 is 162. 5 times 27 is 135. Minus 12 plus 8. And finally, I get to my solution. When I put all that into the calculator, I get 23. So it is quite a bit of work. There's several steps here, but I want you to show your work as you're doing these and just plug in the number. So when you get ready to do part B or problem B, you're going to plug in -2. All right, so write in -2 each time you see x and make sure you multiply it the correct number of times because of the exponent. So I'm going to do problem C here for you. And in this one, we want to use -0.5. Well, this is also the same as saying -1/2. All right, so in case you didn't convert the decimal, that's just -1/2. So I'm going to plug in -1/2 every time I see an x. And so this time it's -2 times -1/2 to the 4th plus 2 times -1/2 to the 0 power. And all I have to do really for this, remember this, anything to the 0 power ends up being the number 1. Okay, so 1 times 2 is 2. 2 times 1 right here ends up being 2. When I use my calculator and I get, sorry, let me start this here, -1/2 equals -2, and -1/2 to the 4th is 0.0625. All right, I probably should have worked left to right, but that 0 kind of caught me there and made me want to say what I wanted to say about that, so I apologize if I mixed you up there. So at the very end, when I put all this into my calculator, I end up with 1.875. Okay, so here's my final answer. And that's called direct substitution, meaning that we're taking the value that they gave us and we're plugging it in for each time we see the letter X. And I would like you to finish, remember you're finishing the 6 problems at the top, and then I'm also asking you to do problems B and D at the bottom of the page. Please make sure you write down any questions you have, and we will answer those in class when I see you.